Hello everyone, good morning. Myself, Dr. Shubhankar Sen, an associate professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the second lecture of the first week for the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's lecture, we shall cover the following topics. We shall begin with Introduction to Tensors, then we shall briefly discuss on Cartesian tensors, basic operations of tensors. Next, we shall go for differential operators, and finally, we shall provide certain examples of tensors from the thermofluids. Let's first go to the introduction to tensors. So, tensors are quantities of which scalars and vectors are special cases. The concept of tensors can be explained with respect to the case of the definition of stress tensor at a point. So if we go to the definition of stress tensor at a point, we define it. The force per unit area represents the stress at a point. So we can go for the definition. Sigma equals to force per unit area. So in this expression which I have written, that is not for a point, it is in the global sense. So we can use this definition, sigma equals to force per unit area. Here if we note that force is a vector quantity and area is also a vector quantity. So in the definition of stress tensor, we come across a situation where we divide a vector by another vector, but the division of two vectors is undefined, and similarly we shall show later that division of two tensors is also undefined. Under such cases, we can rewrite this expression as F bar equals to sigma A bar. Now in this expression F equals to sigma A bar, sigma is a quantity which should take the directions of both force and area. So when the directions of force and area they become same, we get a normal stress, and when they are perpendicular to each other, we get a shear stress. It means that sigma represents a quantity which assumes magnitudes as well as multiple directions. In this case, we have the directions of two quantities, direction of force which is a vector as well as direction of area which is another vector. So two directions are associated with the stress tensor. Because of that, we say that stress tensor is a second order tensor. Using the tensorial or indicial notation, this algebraic expression cast in vector form can be written as Fi equals to sigma ij aj. So we should note that the vector quantities are also known as coordinate free quantities. The vectors are independent of any coordinate system. Okay, so when we write V bar, we can write in component form V1, V2, V3. Now these V1, V2, V3, they can be components in Cartesian coordinates, they can be components in cylindrical polar coordinates, or they can be components in spherical polar coordinates or any such coordinate systems. So here we are getting the sigma is a stress tensor which is having two independent indices I and j. We say that I and j are free indices, and because of that sigma is a second order tensor. So in a quantity, if we have no free index, then we say that it is a scalar quantity. So for example, if we simply write the number 5 or if we write the letter a, then we get a scalar quantity. Now if we write aii, in this case aii is having two indices. It is the same index, it has been repeated two times. Now in this case we cannot say that I is a free index. Here I serves as a repeated index or as a dummy index. Because of repetition, I does not, here I is not considered as the free index and aii is considered as a scalar, not as a second order tensor. Okay, so this should be very clear that if the indices are repeated, then it gives a scalar quantity, and if the free indices are present, we get a tensor quantity. So a vector is a first order tensor, a scalar is a zeroth order tensor. In reality, in real life, we get a maximum tensor of fourth order, that is the elastic constant, which is a fourth order tensor. Mathematically, we can have an nth order tensor, where n is an finite number. Now, a tensor, if its order is n, so we say that order is also known as rank. Order or rank of the tensor is n. Then, if we go for the dimensionality of the problem, the dimensionality, or we say dimensionality is also known as range, then we say this is denoted by r. Then the tensor will have range to the power rank equals to r to the power n components. So if we go for the stress tensor, for the stress tensor, the rank is n is 2. If we go for in 3D, r is 3. So sigma ij or sigma double bar represents for two indices, for two directions of every component. So sigma double bar will have 3 to the power 2 or 9 components in 3 dimensions. Now, these 9 components of 3 dimensions in 3 dimensions, they can be written as sigma double bar equals to sigma ij. We can write it as summation over I equals to 1 to 3, summation over j equals to 1 to 3, sigma ij, ei cap, ej cap. Now this ei cap, it is a unit vector, and ei cap, ej cap together, they form a dyad that is used for defining the directions associated with a tensor quantity. It should be noted that ei cap, ej cap is not equals to ej cap, ei cap. So I have told that the tensors are higher order quantities for every quantity, every component of which we have multiple directions. Next we go for the Gibbs notation for tensors. This Gibbs notation is the presentation in vector form. So if we consider the vector V bar, it can be represented using indicial or tensorial notation as Ui. Using this Gibbs formulation, we can write it as summation over I equals to 1 to 3 Ui ei cap. So we can write it as U1 E1 cap plus E2 U2 E2 cap plus U3 E3 cap. Here E1 cap, E3 cap, E2 cap, they form a basis in 3 dimensions. They are unit vectors and they are linearly independent. Similarly, this is the case for the first order tensor V bar. If we go for the second order tensor, as for example the stress tensor, then we can write it as sigma bar equals to sigma ij equals to double summation of sigma ij followed by unit dyad ei cap, ej cap, where I equals to 1 to 3 for example, and j equals to 1 to 3. If we expand it, we can write it as sigma 1 E1 cap E1 cap plus sigma 1 2 E1 cap E2 cap plus sigma 1 3 E1 cap E3 cap plus sigma 2 1 E2 cap E1 cap plus sigma 2 2 E2 cap E2 cap plus sigma 2 3 E2 cap E3 cap plus sigma 3 1 E3 cap E1 cap plus sigma 3 2 E3 cap E2 cap plus finally plus sigma 3 3 E3 cap E3 cap. As I have mentioned, this ei cap ej cap, this is a dyad and we cannot change the positions. Similarly, ei cap ej cap ek cap, they form a triad and they are used for the third order tensors. Next we go for the Cartesian tensors and the Kronecker delta operator. So in the real number three-dimensional Euclidean space, a Cartesian tensor is represented in terms of orthonormal basis vectors. So in the Cartesian coordinate system x, y, z, we can show the unit vectors e1 cap, e2 cap, e3 cap. Here O is the origin, so the position vector of a point P, this can be represented by the symbol OP bar, or if we say it is A bar. So we say that this is the x1 coordinate. So coordinate of point P is x1, y1, z1. So we are showing the components. Now here A bar equals to x1 e1 cap plus x2 e2 cap plus x3 e3 cap equals to summation over xi ei cap, where I varies from 1 to 3, equals to xi ei cap. Here the indices are repeated. The repetition indicates summation. This also comes from Einstein's summation convention. Now the orthonormality property of these basis vectors e1 cap, e2 cap and e3 cap, they are represented by the Kronecker delta operator. So we can write it that ei cap dot ej cap equals to ej cap dot ei cap equals to delta ij, and in 3D delta ij can be written as delta 11, delta 12, delta 13, delta 21, delta 22, delta 23, delta 31, delta 32, delta 33. So this is a 3 by 3 matrix with the terms as 1 0 0 0 1 0 0 0 1. So Kronecker delta's definition is clear from here, that if I equals to j, delta ij equals to 1, those terms come along the diagonal, and if I not equals to j, delta ij equals to 0, and they construct the off diagonal terms of the Kronecker delta matrix, which is actually the identity matrix or the unit matrix. So here we have shown that ei cap dot ej cap, this is commutative for dot product equals to ej cap dot ei cap equals to delta ij. So delta ij is known as the Kronecker delta operator. So here we shall mention certain features of the Kronecker delta operator. Delta ii, it represents summation over I equals to 1 to 3 in 3 dimensions. So it gives us delta 11 plus delta 22 plus delta 33. Now from this matrix we find delta 11 equals to 1, delta 22 and delta 33, they are also having unit values. So summation ultimately gives us 3. Then if there is a vector x, we can say that xi, then this is one property of Kronecker delta. So a row vector is converted to column vector or vice versa. So this is xi delta ij equals to xj. The third property is then the fourth property we can write ej cap dot x bar equals to ej cap dot xi ei cap. Then we can write it as xi ej cap dot ei cap equals to xi ei cap dot ej cap equals to xi delta ij equals to xj. And the fifth property we can write it as inner product or dot product of first order between two vectors u and v. We can write it as ui ei cap dot uj ej cap. This gives us ui uj into ei cap dot ej cap equals to ui uj into delta ij equals to ui ui. So this ultimately gives us a scalar quantity. This gives us u square plus v square plus w square if u equals to if u bar equals to v bar. Under basic operations of tensors, we discuss the addition, subtraction, product, and division of tensors. First, we consider the addition and subtraction of tensors. Addition and subtraction operations of two tensors are possible if they are of the same order. Operations between tensors of the same order. For example, if we go for two vectors ai and bi, if we add them, the result if it is ci, then this is possible because all of them are vectors or of the same order. Similarly, we can write aij minus bij equals to cij. Next, we go for the product of tensors. There are different kinds of products of tensors. The first one of them is the inner product, which sometimes in vector calculus we used to define as the dot product. So this inner product, it is commutative. So let us consider two vectors a and b, and let us take the inner product of these two quantities. This can be written as a dot b equals to ai bi equals to a1 b1 plus a2 b2 plus a3 b3 in 3 dimensions. So a dot b, it can be written as a transpose b equals to a1 a2 a3 as a row vector in b1 b2 b3 as a column vector. This gives us a scalar or a 1 by 1 matrix. Next, we go for the inner product of higher order. So here we can discuss the gradient of velocity vector and the stress tensor sigma. Both are second order tensors, and we can take inner product of these two quantities. So that is denoted by the symbol double dot product, gradient of v, double dot product sigma. So this gives us a scalar quantity. Output is a scalar quantity. So gradient of v double dot sigma equals to del u I del xj sigma ij, which can be written as summation I equals to 1 to 2 summation j equals to 1 to 2 in 2 dimensions del uy del xj sigma ij equals to summation over I equals to 1 to 2 del ui del x1 sigma i1 plus del uy del x2 sigma i2. We can expand over I, then we get del u1 del x1 sigma 1 1 plus del u2 del x1 sigma 2 1 plus del u1 del x2 sigma 1 2 plus del u2 del x2 sigma 2 2. So we can write it using the conventional symbols. U1 stands for u, x1 stands for x, and in that way we can write it as del u del x sigma xx plus del v del x sigma yx plus del u del y sigma xy plus del v del y sigma yy. Next, we define the contraction operation of inner product. The contraction operation is one kind of operation where a third order tensor reduces its order by 2 and becomes a first order tensor. Consider a third order tensor aijk. So by performing the contraction operation, it can be reduced to a vector ck. So we say that ck equals to delta ij aijk. So this kind of an operation where the third order tensor reduces its order by 2 and becomes a first order tensor is known as a contraction. So the tensor aijk, it can be having the following forms: aiik, aijj, etc., etc. These both of them are vectors, and these are the examples of contraction operation. Next, we go for the outer product. So outer product of two tensors. Let us consider product of two tensors. The first one's order is m and the second tensor's order is n. Then their output will be a tensor of order m plus n. So first tensor of order m, second tensor of order n, it will give a new tensor of order m plus n. So outer product is not commutative. So this is the symbol of outer product. So V, outer product V is a velocity vector. This is a first order tensor and it is taking outer product with itself. It means that we are getting a quantity which will have m equals to 1, n equals to 1. So m plus n equals to 1 plus 1 equals to a second order tensor. So this output quantity will be a second order tensor. So this V bar, outer product V bar, it can be written as V transpose. So we can write it as Ui Uj using the indicial notation, and then we can write it as UVW with UVW. 3 row 1 column, 1 row 3 column. This will give us a matrix of order 3 by 3. So this gives us U square, UV, UW, V square, VU, VW. Here I mentioned that when we take inner product of two tensors of orders m and n, the output is a quantity of reduced order m plus n minus 2. Next we go for the cross product of tensors. Let us consider one tensor A bar, the next tensor is B bar. They are of the same order, of first order. So if we take the cross product between these two tensors, then we find out a new vector that is denoted by the symbol C bar. Then we write that C bar equals to epsilon ijk aj bk. So now epsilon ijk, this is the alternating tensor. It is having indices ijk. In the right hand side, the remaining terms aj bk contains two indices j and k. So in the left hand side, the free index is I. So the velocity vector C bar, it must have the index I. So we say that C bar equals to epsilon ijk aj bk, where epsilon is the alternating tensor operator. So epsilon we can define, it has the values which will be 1, -1 or 0 based on cyclic or anticyclic or acyclic arrangement of these indices 1, 2 and 3. We shall have epsilon's values. So epsilon 1, 2, 3 equals to epsilon 2, 3, 1 equals to epsilon 3, 1, 2 equals to 1, epsilon 1, 3, 2 equals to epsilon 2, 1, 3 equals to epsilon 3, 2, 1 equals to -1. The first set, the first row, it is for the cyclic permutation of 1, 2, 3. The second row, where we are getting the -1 value, this is for anticyclic permutation of 1, 2 and 3. And similarly, you can get epsilon 1, 1, 2 equals to epsilon 1, 1, 1 equals to epsilon 1, 3, 3 and so on to be equals to 0. This is for the acyclic permutation. Next, we define the scalar triple product. So if we go to the vector calculus, we know about the scalar triple product A dot B cross C. This quantity expression is known as the scalar triple product, which we can write is B cross C. It can be written as epsilon ijk bj ck. Now this is a vector quantity with one free index, that is I, and we shall take the dot product of this vector with the vector I. So for this dot product, we need at least one identical index. So here I is the free index. Here I is the free index. It means that the vector A must be assigned with vector with index I, so that finally we get a scalar. So we get an output quantity as a scalar quantity from the scalar triple product. So A dot B cross C can be written as epsilon ijk ai bj ck. Division of tensors comes next. There is no division operation for tensors and vectors. Actually, this is the root of the concept of tensors. Here, I provide some more information about the inner product of vectors. Let us go for the, I just mentioned it that no division operation is defined for tensors and hence for vectors. For the inner product portion, I give some more information. If there is a tensor of order m and there is another tensor of order n, then when we perform the inner product, the output quantity will have order m plus n minus 2. So mth order tensor and nth order tensor, if we take inner product of these two quantities, they will give an output quantity for one inner product, which will be of m plus n minus 2. So when we take a dot product between A and B, then for A, m is 1, for B, n is 1. So it means that m plus n minus 2 equals to 0. We get a 0th order tensor or we get a scalar. So A dot B is a scalar, which is a 0th order tensor, and it is coming according to this expectation given by this m plus n minus 2 formula. Now, if we consider the dot product of a vector and a second order tensor, so we consider the stress tensor sigma, and you take the projection of the stress tensor normal to the surface, then we say that this is n dot sigma. So n is the unit vector. So the projection of the stress tensor normal to the surface is known as the surface traction vector. So we say this is h bar. So in our fluid mechanics problems, when we go for numerical treatment, we use the traction-free boundary conditions. This traction, which is a force, is denoted by the symbol h bar. this is a vector. So this inner product n dot sigma, it gives us a vector quantity. For n, our m is 1 for n, and for sigma, n equals to 2. So our output quantity should be m plus n minus 2. Output quantity should be 1 plus 2 minus 2. Output quantity should be of first order. So the output should be a vector quantity, and we get that the stress tensor and its projection, it is giving us the surface traction vector, which is the first order tensor, or which is a vector. We can simplify this expression for n dot sigma as Hj equals to Ni sigma ij, which can be written as Hj equals to Nx sigma xj plus Ny sigma yj. So there is less space here. I just write this expression at the corner here. Some space I can find here. So I can write it here that Hj equals to Nx sigma xj plus Ny sigma yj. This gives us in two dimensions hx and hy as hx equals to nx into sigma xx plus ny into sigma yx. And the second item hy, the second component, this is nx sigma xy plus ny sigma yy. Now this nx and ny quantities, these are the direction cosines. These are the components of the vector, unit vector n cap. Nx and ny, they are direction cosines or components of the unit vector. So here we can write that nx cos theta, ny equals to sin theta. If this is the surface, this is the unit vector n cap, then we say that this x component, this is nx, this is ny, and this is the angle theta. So this is a surface. So because of space, I could not show it properly, but you remember that nx, ny and nz, they are the components of unit normal surface. Then nx is ny and nz are known as the direction cosines, and they are shown in this sketch. I have shown nx and ny. Nx is cos theta and ny is sin theta. Next we discuss on various differential operators using tensor notation. The basic differential operators are the gradient operator, the divergence operator, and the curl operator. So we can take gradient of a vector, gradient of a tensor, divergence of a vector, divergence of a tensor, or curl of a vector and tensor. So first we discuss on the gradient of a vector. So let us first discuss on the gradient operator. So gradient operator is denoted by the symbol del bar, which is actually the Nabla operator, which we write it as del xi. So if phi is a scalar quantity, which is a function of x, y, z, for phi, the gradient of phi, which is a vector quantity, it is written as del phi del xi. If we consider gradient of a vector, then consider the vector velocity v bar. If we take the gradient of this vector, then we write it as grad v bar. This becomes the velocity gradient tensor. The gradient operator increases the rank or order of the quantity by 1. So the velocity vector, which is a first order quantity, it becomes a second order vector, or it becomes a second order tensor. So gradient of v bar, we can write it as So gradient of vector, it can be represented in matrix form. It has 9 components in 2 dimensions, in 3 dimensions. Del u del x, del u del y, del u del z. Then you can write again second row, del v del x, del v del y, del v del z, and del w del x, del w del y, del w del z. So this is the velocity gradient tensor with rank 2. Next we go for the divergence operator, which operates on a vector or a tensor of order 1 or more than that. So let us go for the divergence of the velocity vector. So divergence operator symbol is del dot. So when it operates on the velocity vector, we can write it as del of v bar equals to so we get a scalar quantity. So what is happening? The gradient operator, it was increasing the order by 1, and in contrary, the divergence operator reduces the order by 1. So we can write it as, by the summation formulation in 3 dimensions, del u1 del x1 plus del u2 del x2 plus del u2 del u3 del x3, which is a scalar quantity. Next we define the curl operator. So curl operator operates on vectors and tensors. So this curl operator is denoted by the symbol del cross. So if we consider a vector v bar and if we take curl of this vector, then we can write it as so curl of a vector is represented as epsilon ijk del vk del xj, where the quantity epsilon ijk is known as the alternating tensor. Next we go for the Laplacian operator. The Laplacian operator, which is a scalar operator, is denoted by the symbol del square. This is obtained by taking inner product of the nabla operator with itself. So this Laplacian, we can represent it as del square equals to del bar dot del bar equals to del del xj del del xj. So it can be written as del 2 del xj del xj. So the fourth order operator, it can be simplified as del 4 equals to del square operating on del square, del 2 del xj operating on del 2 del xi del xi. Next we go for the divergence of the stress tensor. Now we know that stress tensor is a second order tensor. If we take divergence of it, the output quantity will be a first order tensor or a vector. So let us write it in this manner. The stress tensor sigma double bar, we can write it as sigma ij. Then if we take divergence of sigma, we get del del xj of sigma ij. It gives us del sigma ij del xj. So we can see here that only I is the free index in the expression del sigma ij del xj, and because of that, this output quantity, it represents a vector quantity. Let us consider this vector is c. So we can write it as Ci equals to del sigma ij del xj. In 2 dimensions, we can write C1, C2 equals to del sigma 1 del x plus del sigma 1 del y, and the second component C2, this can be given by del sigma 2 del x plus del sigma 2 del y. Now representing 1 by x and 2 by y, this vector can be written as del sigma xy del y, del sigma yx del x plus del sigma yy del y. So in this expression, what I did, first this j was the repeated index, so I have performed the summation over j. So once it was j equals to 1, so when j was 1, j was varying from 1 to 2. So x1 means del x, x2 means y, so it is y. And if we go for the second term, so in that case, I was 2, so it was sigma 2 and sigma 2, and here j was varying from 1 to 2. So this expression is okay. And next we go for the convective operator or special acceleration operator. In the momentum equations, we get the acceleration term in the left hand side. Here we have 2 parts, one unsteady part or temporal part and one spatial part or the convective part. So this convective acceleration, we generally write it as v bar dot del operating on v bar. So here v bar dot del is the convective operator. In this expression, we say that the v bar within the bracket, it is the convective velocity, and v bar outside, this is the convected velocity. So this is a nonlinear term, this full expression. So this v bar dot del, this operator, this can be written as uj del xj. And when we are putting v bar dot del, it is operating on the velocity vector itself, then we get it at uj del uy del xj. So in this expression, we see that I is the free index and j is the dummy index, and because of that we say that this is a first order tensor or a vector. It should be remembered that divergence of velocity and v bar dot del, they are different quantities. So this del dot v is not equals to v bar dot del bar, else the continuity equation for incompressible flow, it will be just meaningless. Okay, so this is a very important observation that these two quantities, they are different. Next we go for the material derivative operator. This is also present in the left hand side of the momentum equation, or the continuity means, or the continuity also we can say, and the energy equation. So this material derivative operator, it is given by the time component and the velocity component. So here the material derivative operator is written as the total derivative. So it is given by capital D dt equals to temporal derivative plus the convective portion. So it is operating on a scalar or a vector. So here this V bar dot del, the convective operator, we have already written as uj del del xj. So if we combine, we can write the material derivative operator as d dt equals to del del t plus uj del del xj. Now this operator, this can operate on a scalar or a vector. This is also known as the substantial derivative. Next, we provide the expressions for inner product of second order. So inner product of second order, it is possible for tensors of order 2. Let us consider the stress tensor sigma and the strain rate tensor epsilon. Both of them are second order tensor. So if we want to take a dot product between them and we want a scalar quantity as the output, then we can write the product with this symbol, that sigma double dot product epsilon. So this is the symbol of double dot product, or we say that this is an inner product of higher order. So we know that in the dot product, we must have the identical indices in both of these quantities. So this we can write at sigma ij epsilon ij. So ultimately, there is no free index. There is no free index in this expression. So output must be a scalar quantity. So if we just try to expand sigma ij epsilon ij sigma double dot product epsilon equals to sigma ij epsilon ij, and if we do this expansion in 2 dimensions, we can write it as sigma i1 epsilon i1 plus sigma i2 epsilon i2. This is expansion over j. Now in the next step, we perform the expansion over I. Then we get it like sigma 11 epsilon 11 when I equals to 1. When I equals to 2, then we get sigma 21 epsilon 21. For the second portion, when I equals to 1, we get sigma 12 epsilon 12, and when I equals to 2, we get sigma 22 and epsilon 22. Now replacing 1 by x and 2 by y, the final expression will be sigma xx epsilon xx plus sigma yx. Here it was sigma 21 epsilon 21, so it is sigma yx epsilon yx. The next term is sigma xy epsilon xy sigma yy epsilon yy. So these quantities, ultimately this becomes a scalar quantity. So this we can represent with respect to double summation, summation over I and summation over j, where I is varying from 1 to 2 and j is varying from 1 to 2 in 2 dimensions. So we could have shown this in 3 dimensions also. This directional derivative operator, it comes in the derivation of the weak form in the right hand side. It contains the flux term which acts at the element interfaces. So directional derivative operator, this is given by the symbol del del n. So if we go for 3 dimensions, del del n can be written as nx del del x plus ny del del y plus nz del del z, where nx, ny and nz, they are the direction cosines of the normal n cap of the surface. So n cap, this is the normal to the surface. It has 3 components, nx, ny and nz. This nx, ny and nz, they are the direction cosines. Now we provide some examples of tensors that come in thermofluids. The first example is the thermal conductivity. In most of the cases, we treat the thermal conductivity as a scalar quantity. So if we go for pointwise distribution of thermal conductivity within the material, it is actually a second order tensor. So thermal conductivity denoted by the symbol K, it can be written as a second order tensor K double bar, and in 3 dimensions we can write it as the thermal conductivity tensor in 3 dimensions. It has 9 components: Kxx, Kxy, Kxz, Kyx, Kyy, Kyz, Kzx, Kzy, Kzz. It means that the thermal conductivity shows directional properties. Now, if the material is homogeneous and isotropic, then for isotropic material, we define that Kij equals to 0 if I not equals to j. It means that the off-diagonal components of this thermal conductivity tensor, they vanish for the isotropic material. Along with this, the diagonal terms, they become same when I equals to j. With this condition, the thermal conductivity tensor, it simplifies to K 0 0 0 K 0 0 0 K, and this permits us to consider thermal conductivity as a constant with a single value everywhere. Next, we give the example of velocity gradient. So velocity gradient tensor we have already defined. So it is gradient of V bar, which is a second order tensor. This is a second order tensor. So velocity gradient tensor is del u by del xj, and already we have expanded it in the matrix form, that it has 9 components in 3D. And momentum flux tensor, this is also a second order tensor. This appears in the left hand side of the momentum equations or the Navier-Stokes equations. The momentum flux tensor, it is represented by the symbol rho V bar outer product V bar. So the momentum flux tensor can be written as rho V bar V transpose. So this symbol is the symbol of the outer product. We can write it as rho ui uj using the tensorial notation. So in matrix form, we can represent it as rho u v w as the column vector, where u v w are the components of the velocity vector, and then the transpose of this velocity vector is u v w as a row vector. Then from here we get the final matrix rho into u square, u v, u w, v u, v square, v w, w u, w v, w square. This is the momentum flux tensor, and if you see here, the first row, these terms, they appear in the left hand side of the x momentum equation. The second row, these terms appear in the left hand side of the y momentum equation, and similarly the third row appears in the left hand side of the z momentum equation. Next we go for the stress tensor. This is the basic tensor which comes in solid mechanics and fluid mechanics both. So stress tensor, the second order tensor, this is represented as sigma ij. So using the Gibbs notation, we can write it as sigma double bar equals to summation over I equals to 1 to 3, summation over j equals to 1 to 3, sigma ij. Then we consider the dyad E I cap, E j cap, and we have the 9 components of sigma double bar in 3 dimensions: sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. These are the components in 3 dimensions. And finally, we have the strain rate tensor. This is denoted by the symbol epsilon double bar or epsilon ij. So strain rate tensor is defined as the average of the velocity gradient tensor and its transpose. So epsilon double bar equals to epsilon ij equals to average of velocity gradient tensor and its transpose. So it is written as half of del ui del xj plus del uj del xi. So here we conclude today's lecture. The tensors are means of representing the equations in a very compact and brief manner. The tensor product which we have discussed in today's class, it will be found later that this product is used in evaluating the shape functions as well as determining the elements of higher order Lagrangian elements. In finite element discretization, the element level matrices and vectors are represented in tensorial form and also using matrix and vector forms. So for today's class, the following references I suggest: Rutherford Harris's book, published by Dover Publication. It is titled Vectors, Tensors and the Basic Equations of Fluid Mechanics. Then the appendix of the classic book on turbulence by Stephen B. Pope. I suggest that book. And in the incompressible flow authored by Panton, there is a chapter where we get discussions on vectors as well as tensors. Thank you very much for attending today's lecture.